Hi, welcome to the video that is technically part 2 of ionic bonds. Instead of doing monoatomic ions, we're going to do polyatomic ions today. I know it's been overkill, but let's just do a quick review. Remember, an ion is a charged element. There are two types of ions we can have. We can have a cation and an anion. Cation is positive, anion is negative. Ions form because most elements want to have a full valence shell or a full energy level. In the previous lesson, we learned about monoatomic ions. Monoatomic ions, again, mono means one atom that is charged, or one element that is charged. In this video, we're actually going to talk about something called polyatomic ions. Poly means more than one atom that is charged. And for this video, really important, you will need your polyatomic ion list. If you don't have it from last week, the sub has copies for you. Let's just look at the polyatomic ion list. It looks like a huge table. You are not responsible to memorize all of this. I will give it to you for any mini quiz or any lab assignment that you have. But what do these mean? On the table, you'll see something that says name and something that says formula. I'm actually not sure if it says name or formula. But you will see ammonium and something like NH4 plus. You also might see something that's like hydroxide, which is OH minus. Okay, let's blow this up because this is kind of the most important part. If we have something like NH4 plus, it means that this entire molecule of elements has a +1 charge. Okay, same thing with OH minus. OH is a molecule. It also has a -1 charge. Okay, so it's not just hydrogen that's charged. It's not just the ending. The entire thing is charged. Okay. If you have more than one polyatomic ion, so like let's say we have NH4 plus, but our goal is to get to +3. Okay, that means we need 3 NH4s to get to +3. You see how these charges add up to +3? The way that we do this, the way that we write all of this down, is we write NH4, we put it in parentheses, and we write 3. If we wanted to get OH minus to -4 or something like that, that means that we need 4 OH minuses. Again, we don't want to write like just OH4. We want to put this in parentheses and write 4. Okay. I know I didn't write a charge here, but we should know that this is positive, this is negative. I didn't write a charge. Again, we're only doing this so that we can balance it out with other ions. Okay, so let's look at some examples. Let's look at something, and again, same kind of concept. We're going to be looking at like names and formulas. If we're writing the name of a polyatomic ion, the name doesn't change. So, same kind of thing. We write the cation first. This would be positively charged. The anion second. Regardless if it's monoatomic or polyatomic, the cation name doesn't change. The anion, if it's, put it over here, if it's monoatomic, remember the ending changes to IDE. If it's polyatomic, it doesn't change. Okay, let's look at some examples of just naming. Okay, so let's say we have something like NH4Cl. Okay, and let's do something like LiOH. Okay, here we know that ammonia, or we know that NH4 has to be a polyatomic ion because there's two of them in front of chlorine. We know that this is NH4 plus, and this is Cl minus. We just got that from the periodic table. Same thing here. We have lithium plus. This is monoatomic. This is polyatomic. So circles are mono, squares are poly. And we know that OH has a -1 charge, and you can look this up on your table. I got these from the handout or the table that I gave you guys. When we name these, again, cation name doesn't change. So we look up the name for NH4. This is ammonium. And then we change the ending to IDE if it's mono, so it's chloride. Okay? Cation name never changes. We have lithium. We look up what OH minus is. It's hydroxide. You don't need to write the charges in here because we assume that if it's done correctly, the charges will balance. Okay? If we're writing the formula, that's when we use the parentheses and the subscripts or things like that. So let's do some examples. Let's give you the name and let's do a formula. Let's do strontium perchlorate, and let's do potassium carbonate. Okay. Strontium, if you look on the periodic table, is Sr2+. Perchlorate on our polyatomic ion list is ClO4-. Potassium on the periodic table is +1. Carbonate is CO3 2-. Same exact way that we did it with the monoatomic elements. We have a 2+ here and a 1-. So that means that we need 2 perchlorates in order to balance with that strontium. So I need 2 perchlorates. This is going to add to -2. We want these to be equal and opposite. Okay. Same thing down here. We have +1 and -2. So we actually need 2 potassiums. This is going to add up to +2. This is -2. The way that we write the formula for this is we just write the element symbol and then we write the polyatomic ion. No charges. We assume that the charges are balanced, and in this case, and we need to put perchlorate in parentheses and put a 2 down here. Now the charge is balanced. Sorry if that wasn't clear. At the same time, let's do the next one. So we have 2 potassiums and 1 carbonate. No charges. We assume that they balance. If there's 2 potassiums, it's +2. Carbonate is -1. Okay. Polyatomic ions can be a little bit tricky sometimes. But that's why we practice. And then last thing, if we have a transition metal, it's the same thing that we learned last time, but let's put it in conjunction with a polyatomic ion. Remember, transition metals are always positive. They're always cations. They're always positive. But in this case, you might see it 2 ways. You might be given the name, or you might be given the formula. Okay. If you're giving the name, it might have a Roman numeral in there. So let's do osmium 4 IV bicarbonate. Okay, so we have osmium. We know the charge of osmium. It's in the parentheses. Osmium's a transition metal, so we don't know the charge unless it's given to us. We only know the charge really in the name, and bicarbonate is HCO3 minus. Okay. Again, imbalance of charge here. We need to somehow get this to -4, or we need to somehow get this to -1, which is not possible. So that means that we need 4 bicarbonates to get to -4. So again, the way that we write this, we want to keep this 1-to-4 ratio. We're just going to have 1 osmium, but we're going to put bicarbonate in parentheses out of 4. This is +4. Because we have 4 of these, it's -4. Okay. If you were given the formula for something, let's say it was CO3N2. This is where it can get a little bit tricky. So now we're going from formula to name instead of going from name to formula. We don't know the charge on cobalt. Cobalt is a transition metal. It could be anywhere between +1 to +10. But we do know the charge on nitrogen. Nitrogen is -3. There's 2 of them, so the overall charge is -6. We want whatever cobalt is to equal +6. Okay, but we have 3 of them. So basically, we're doing the charge times 3 equals 6. This means the charge has to be +2. Okay. Now this is important because we need to put this in Roman numerals when we write the name. So we're going to write the name of the transition metal, cobalt. In Roman numerals, we're going to write the charge, which is 2. And then nitrogen is a monoatomic element. So remember, we have to change the suffix to IDE. Let's just do one more. Let's do a couple more, actually. Let's do CuSe, and let's do Cu4Se2. Okay, Cu is copper. We don't know the charge on copper, but we do know the charge of selenium. We know that's -2, so copper has to be +2. So it's copper 2 selenide. Okay, here we know the charge on selenium's -2. We know we have 2 of them, so we're going to multiply by 2. We have -4. We have 4 coppers, so each of these must be +1. If we have 4 of them, that's going to give us plus 4. So we do it for the individual copper. So copper 1 selenide. Sometimes if the charge on the transition metal is 1, you'll see it just as copper selenide. If there's no Roman numeral, you can assume that it's 1. We'll do a lot more practice on this. Do your best on the activity in the worksheet today, and I can review this the day that we get back from Thanksgiving.